Welcome to Earthly Teachings, where learning is clear and powerful. Today we are working on Mathematics N6. Let's learn together. In this video, we'll be diving deep into first-order linear differential equations. We'll start by understanding what they are and the general method for solving them. By the end of this session, you will be able to, first, identify a linear differential equation. Second, find the integrating factor, which is the key to solving these equations. Third, solve for the general solution. And finally, use initial conditions to find a particular solution. We will walk through many examples from Activity 4.1, explaining every step in detail. So grab your notebook and let's get started. First, let's define what we're dealing with. A first-order linear differential equation is any equation that can be written in the form die and dx plus a function of x times y equals another function of x. Let's break that down. First order means the highest derivative is the first derivative, di by dx. Linear means the dependent variable y and its derivative di by dx are raised to the power of 1, and they are not multiplied by each other. The functions p of x and q of x can be any functions of x. Now, how do we solve an equation like this? The key is to introduce something called an integrating factor. The integrating factor, which we'll denote with the Greek letter mu of x, is calculated using this formula. It's the exponential of the integral of p of x dx. Once we have this factor, we multiply our entire differential equation by it. The magic is that the left side will always simplify into a perfect derivative. Specifically, it becomes the derivative of the product of our integrating factor and y. This transformation is what makes the equation solvable. Now we can integrate both sides with respect to x. This gives us the integrating factor times y equals the integral of the integrating factor times q of x dx, plus our constant of integration, c. Finally, we isolate e to get the general solution. Y equals 1 over the integrating factor times the integral of the integrating factor times q of x dx plus c. This is our step-by-step method. Step 1. Write the equation in standard form. Step 2. Find p of x and q of x. Step 3. Calculate the integrating factor. Step 4. Plug it into the general solution formula. Step 5. Solve the integral. And that's it. All right, let's put this into practice with our first example. The problem is, determine the general solution for di dx plus x equals x cubed. Let's follow our method. Step 1, identify p at x and qx. The equation is already in the standard form, di by cex plus pxy equals qx. So ppec is x, the coefficient of y, and qx is x cubed, the term on the right side. Step 2, calculate the integrating factor. The integrating factor mu of x equals e to the integral of pe, which is e to the integral of x d. The integral of x is x squared over 2. So our integrating factor is e to the power of x squared over 2. Remember, when calculating the integrating factor, we don't include the constant of integration for the inner integral. We only need one constant for the final solution. Step 3, apply the general solution formula. I equals 1 over our integrating factor, e to the x squared over 2, times the integral of the integrating factor times q of x, which is e to the x squared over 2 times x cubed, e plus c. Now for the trickiest part, solving the integral. The integral is x3 ex2 sur 2 dx. This requires a combination of a u substitution and an integration by parts. Let's start with a substitution. Let u equals x squared over 2. Then du equals x dx. Our integral becomes e to ex squared, du. Now we need to get rid of the x squared. From our substitution, we know u is x squared over 2, so x squared is 2u. The integral simplifies to 2u iu du. Now we use integration by parts with v equals 2u and dw equals eu du. The parts are v equals 2u, dv equals 2 du to du equals ehu, and w equals eiu du. Applying the formula for integration by parts, which is vw minus the integral of w dv, we get 2u ew minus the integral of ew du. Plugging back in our u and multiplying by 2, the integral is 2 sax 2 2 ishaka 2. 2 equals 2 ko 2, which simplifies to x2 as ex2 to 2. 2e x2, 2. So, the result of our integral is e to the x squared over 2 times the quantity x squared minus 2. Step 4. Substitute this back into our general solution formula. I equals 1 over e to the x squared over 2 times the integral result plus c. Distributing, we get y equals x squared minus 2 plus c times e to the negative x squared over 2. And that is our final answer, the general solution. It includes a constant of integration, c, because it represents a whole family of solutions. Notice the problem asked for the general solution, so we stop here. Let's move on to the next problem, which has a similar structure. We need to find the general solution of di dx plus 2y equals e to the power of 2x times cos. First, is it in the standard form? Yes, it is. So p is 2, the constant coefficient of y, and qx is e to the 2x cos. Next, the integrating factor, mu of x equals e to the integral of p ex dx, which is e to the integral of 2 de. The integral of 2 is 2x. So our integrating factor is e to the 2x. Now, let's plug this into our general solution formula. I equals 1 over e to the 2x times the integral of e to the 2x times qx, which is e to the 2x cos x dx plus c. Notice that e to the 2x times e to the 2x is e to the 4x. The equation becomes y equals e to the negative 2x times the integral of e to the 4x dx cos x plus c. Now we need to solve this integral. This is a classic integration by parts problem that needs to be done twice. Let's set I equal to the integral of e to the 4x cos x dx. For the first part, let v1 equal cos x and db1 equal e to the 4x dx. The formula gives us I equals v1 minus the integral of w1 dv1. This is 1/4 e to the 4x e as x plus 1/4 times the integral of e to the 4x sin x d. Notice we've gone from cos to sin. We need to apply parts again to the new integral. For the second part, let v2 equal sin x and db2 equal e to the 4x dx. We find that the integral of e to the 4x sin x dx is 1/4 e to the 4x sin x minus 1/4 times the original integral I. Now we substitute this back into our equation for I. This gives us I equals 1/4 e to the 4x qsx plus 1/4 times the result of the second part, which was 1/4 e to the 4x sin x minus 1/4 I. This is the trick. The original integral I appears on both sides. Simplifying, we get I equals 1/16 e to the 4x cos x plus sin x minus 1/16 I. We can now solve for I. Add 1/16 I to both sides, which gives 17/16 I. Then divide by 17/16. The integral result is 1 over 17 times e to the 4x times the quantity 4 cos x plus sin x. That was the hardest part. Now, we just need to substitute this back into our general solution formula. I equals it to the negative 2x times our integral result plus c. Distributing e to the negative 2x, we get e to the 2x times 4, cos x plus sin x, all over 16, plus ce to the negative 2x. And this is the general solution. Remember this pattern for integrals of e to the x times sin or cos bx. You'll need to do integration by parts twice to solve for the original integral. Let's look at another example. This time, we'll need to do some rearranging first. We need to solve ln x di dx plus y over x equals cos x. This is not in standard form. We need di slash dx to have a coefficient of 1, so we'll divide the entire equation by ln x. Now it's in standard form. Px is 1 over x ln x, and qx is cos x over ln x. Let's find the integrating factor. Mu of x equals it to the integral of 1 over x ln x dx. To solve this integral, we can use a u substitution. Let u equal ln x, then do equals 1 over x dx. The integral becomes the integral of 1 over u do, which is ln of the absolute value of u. Substituting back, we get ln of the absolute value of ln x. The exponential e and natural logarithm ln are inverse functions. They cancel each other out, so our integrating factor is simply ln of the absolute value of x. Now we plug this into our general solution formula. I equals 1 over ln x times the integral of ln x times q cux, which is q as x over ln x dx plus c. Look what happens inside the integral. The ln x in the numerator and the denominator cancel out perfectly. This is why the integrating factor method works so well. We're left with the integral of cos x dx, which is sin x, so we have y equals 1 over ln x times sin x plus c. Finally, we can write our general solution more cleanly. I equals sin x over ln x, plus the constant c over ln x. Let's explore an alternative form of these linear equations. The standard form is dx plus p equals qx. But sometimes it's easier to think of x as the dependent variable and y as the independent variable. This results in the form dx/di plus a function of y times x equals a function of y. The solving process is identical, but we differentiate and integrate with respect to y. The integrating factor becomes mu of y equals e to the integral of py. And the general solution for x is 1 over mu of y times the integral of mu of y times q of yd plus c. Let's see an example where this is useful. We have the equation dx di plus 2x equals 1/2 e to the negative 2y cos y. This equation is already in our alternative standard form. P of y is the coefficient of x, which is 2. Q of y is the right-hand side 1/2 e to the negative 2y cos y. The integrating factor, mu of y, is e to the integral of 2di, which is e to the 2e. So mu of y equals e to the 2e. Now for the general solution for x. X equals 1 over e to the 2i times the integral of e to the 2i times our q of y term, d plus c. Inside the integral, something nice happens. E to the 2i and e to the negative 2i cancel each other out, as they are multiplicative inverses. We are left with the integral of 1/2 cos y d. The integral of cos e is sin y, so x equals e to the negative 2y times a 1/2 sin y plus c. Let's distribute the e to the negative 2y to get our final general solution. X equals 1/2 e to the negative 2i sin y plus c e to the negative 2y. This problem was much simpler than the integration by parts example. The key was recognizing that it was already set up perfectly in terms of y, saving us a lot of work. Now let's tackle a more challenging problem, one that requires a change of variable or substitution. The problem is sx squared yd dx plus tan y equals qsx. This doesn't look like a standard linear equation, but the problem gives us a hint. Let t equals tan y. Let's follow that hint. We have the substitution t equals tan y. We need to find dt dx to replace the di dx term. Using the chain rule, dt dx equals dt dd times di li. The derivative of tan y with respect to y is sx squared y. So dt dx equals sx squared y times di dx. Now let's substitute t and dt dx back into our original equation. The term sec squared y dl dx becomes dt dx. The term tan y becomes t. So the equation transforms into dt dx plus t equals cos x. This is a first-order linear equation in terms of t and x. It's now in standard form. Px is 1 and qx is cos. Let's solve for t. The integrating factor is e to the integral of 1 dx, which is e to the x. The general solution for t is 1 over e to the x times the integral of e to the x cos x dx plus c. You'll recognize this integral. It's another case of integration by parts twice. Let's do it quickly. The result is e to the x times the quantity sin x plus cos all over 2. Now substitute this back into our equation for t. T equals 1 over e to the x times the integral result plus c. Distributing e to the negative x, we get t equals 1/2 sin x plus 1/2 cos x plus c e to the negative x. But we're not done. The problem was given in terms of y, so our answer must be in terms of y. We need to substitute back using our original substitution. Remember, t equals tan iy, so we replace t with tan y. The general solution for y is tan iy equals 1/2 times the quantity sin x plus cos x plus c e to the negative x. This example shows the power of substitution. Sometimes, a complicated-looking equation can be transformed into a standard linear one, which we already know how to solve. Now let's shift our focus from finding the general solution to finding a particular solution. A particular solution is found by using an initial condition to determine the specific value of the constant of integration, c. It represents one specific curve from the family of solutions. The process is simple. First, you find the general solution, just as we've been doing. Second, you plug in the given initial condition, a specific x and y value, into the general solution and solve for c. Finally, you substitute this value of c back into the general solution to get your particular solution. Let's work through an example. We need to find the particular solution for dx plus xy equals x cubed, given the initial condition x equals 0 and y equals 1. You might recognize this equation. It's the first problem we solved. The general solution we found was y equals x squared minus 2, plus c times e to the negative x squared over 2. Now we apply the initial condition. X equals 0 and y equals 1. We substitute these values into our general solution. 1 equals 0 squared minus 2, plus c times e to the negative 0 squared over 2. Let's simplify. 0 squared is 0, and any number raised to the power of 0 is 1. So e to the 0 is 1. Our equation simplifies to 1 equals negative 2 plus c. Solving for c, we add 2 to both sides, which gives us c equals 3. The final step is to substitute this value of c back into our general solution. The particular solution is y equals x squared minus 2, plus 3 times e to the negative x squared over 2. This equation no longer contains the constant c. It describes a single curve that satisfies both the differential equation and the given point. 1. Visualizing this, imagine a plane. The general solution is a family of parabolas that are shifted horizontally and vertically. The particular solution is just the one parabola in that family that passes through the specific point, 0, 1. Let's try another particular solution problem, this time with a different form of quadrature. We need to find the particular solution for dx plus y equals x plus 3e to the negative x at the point 0, 1. The equation is already in standard form. P of x is 1, and qx is the quantity x plus 3 times e to the negative x. The integrating factor is mu of x equals e to the integral of 1 dx, which is e to the x. Plugging this into our general solution formula, we get y equals 1 over e to the x, times the integral of e to the x times our qx term, x plus c. Let's simplify the integral. E to the x times e to the negative x is e to the 0, which is 1. The integral becomes the integral of x plus 3 dx. This is a very straightforward polynomial integral. The integral of x is x squared over 2, and the integral of 3 is 3x. So we have x squared over 2 plus 3x. Our general solution is y equals e to the negative x times the quantity x squared over 2 plus 3x plus c. This is our general solution. Now we use the initial condition x equals 0 and y equals 1 to find c. 1 equals e to the 0 times 0 squared over 2 plus 3 times 0 plus c. E to the 0 is 1. The terms in the parentheses are all 0 except for c. So we have 1 equals c. Substituting c equals 1 back into our general solution gives the particular solution. Y equals e to the negative x times the quantity x squared over 2 plus 3x plus 1. Notice the constant of integration c is what allows us to tune the solution to pass through any given point. Once we find that c, we have a unique curve. Let's work through one more particular solution problem, just to solidify the process. The problem is to find the particular solution of dx minus y over x equals x times e to the x, given x equals 1 and y equals 0. First, we get it into standard form. It's already there. We can rewrite negative y over x as negative 1 over x times y. So p is negative 1 over x, and q is x e to the x. Next, the integrating factor. Mu of x equals to the integral of negative 1 over x dx. The integral of negative 1 over x is negative ln x. So our integrating factor is e to the power of negative ln x. Using logarithm rules, we can write negative ln x as ln of x to the power of negative 1. This cancels with the exponential, leaving us with x to the negative 1, which is just 1 over x. Now we set up the general solution. I equals x times the integral of 1 over x times x e to the x dx plus c. Inside the integral, the x terms cancel, leaving us with the integral of e to the x. The integral of e to the x is e to the x. So, our general solution is y equals x times e to the x plus c. Now, let's find the particular solution using the initial condition x equals 1 and y equals 0. O equals 1 times e to the power of 1 plus c. This simplifies to 0 equals e plus c. Solving for c, we get c equals negative e. Now we substitute this value of c back into our general solution. The particular solution is y equals x times e to the x minus e. Let's do a quick check. If we plug in x equals 1, we get y equals 1 times e to the 1 minus e, which is e minus e, or 0. This matches our initial condition, so we can be confident in our answer. Finally, let's look at a word problem that translates into a differential equation. The problem asks for the equation of a curve whose gradient is given by di dx equals x squared minus 2y, all over x, and which passes through the point 1, 2. The first step is to recognize that gradient means the derivative, di x. So we're given the differential equation di dx equals x squared minus 2y over x. This doesn't look like our standard linear form yet. We need to rearrange it. Let's split the fraction on the right side. Di slash dx equals x squared over x, which is x minus 2y over x. Now, let's move the term with y to the left side by adding it to both sides. We get di slash dx plus 2 over x times y equals x. Now it's in our standard linear form. From here, it's the same process we've used before. Px is 2 over x and qx is x. The integrating factor is e to the integral of 2 over x dx, which is e to the 2 ln x. Using log rules, this is e to the ln of x squared, which simplifies to x squared. The general solution is y equals 1 over x squared times the integral of x squared times x dx plus c. This simplifies to y equals 1 over x squared times the quantity x to the 4th over 4 plus c. Distributing, we get the general solution y equals x squared over 4 plus c over x squared. Finally, we use the point 1, 2 to find the particular solution. 2 equals 1 squared over 4 plus c over 1 squared. This gives 2 equals 1/4 plus c. Subtracting 1/4 from both sides, we find that c equals 7 over 4. Substituting this c back into our general solution gives the final equation of the curve. Y equals x squared over 4 plus 7 over 4x squared. Let's quickly review the key concepts we've covered. We learned that the standard form of a first-order linear equation is de dx plus piece y equals cos. The first step is always to ensure the equation is in this standard form. The heart of the solution method is the integrating factor, x equals cos e p cos dx. This factor transforms the left side of the equation into a perfect derivative, which makes it easy to solve by integration. We also saw the alternative form, dat dy plus pyx equals qi, and the power of substitution for more complex problems. Finally, we used initial conditions to move from a general solution, which is a family of curves, to a particular solution, which is a single, unique curve that passes through a specific point. Common traps to avoid include mistakes with the negative signs in PTT, forgetting the logarithm properties for the integrating factor, and integration errors, especially with integration by parts. Always remember to add the constant of integration, c, at the end of your final integral. I encourage you to try the other problems from Activity 4.1 on your own. Practice is the best way to master these techniques. Thank you for watching. I hope this detailed tutorial has helped you gain a solid understanding of solving first-order linear differential equations. Learning is a journey, and every problem you solve makes you stronger. If you found this video helpful, please like, subscribe, and share it with your classmates. Continue learning with earthly teachings. See you in the next video.